Let us look now at interference and diffraction. So remember that when two or more waves meet, they come together, they can interfere constructively, where their peaks line up and then the path length difference between the two waves is an integer number of wavelengths. So here we have one wave, and here we have a second wave. What we mean by the path length difference is the difference in length traveled by one wave and the other. So then we'll say that if L1 minus L2, and that's in absolute value because we might not know which of the waves travels a longer distance, when we want them to meet, we'll say that the path length difference should be equal to an integer number of wavelengths. And in that case, their peaks line up loosely in my drawing, and their valleys line up as well. Then they can also interfere destructively, and that means that their peaks line up with their valleys, and the path length difference then is m plus 1/2 lambda. So if we look at, let's see, this would be half a wavelength, and that is also half a wavelength. So we see that this half is that half shifted over by half a wavelength. So that's where the m plus 1/2 lambda comes in. To go between destructive and constructive interference, all we have to do is shift one of the waves by half a wavelength in either direction, and then they go back to being in phase if they were out of phase, or out of phase if they were in phase. Now let's look at single slit diffraction. Here is an image for that, so let me explain what all of this is. Here is where the slit is, and then light shines from some source and will be bent at the opening here. It will diffract, it will flare out at that point, and waves will go, let's say, like this. Here's one wave, and the other one will start out in phase and end up out of phase when it hits this location, because the bottom wave travels a little bit longer than the top wave. So depending on how much it travels more, it looks like half a wavelength, then when it hits the screen here, it will interfere destructively. In the middle here, let me change the color of my pen. So if I get a wave traveling here to the center of the screen from both openings, for both sides of the opening, they will interfere constructively at that point because they both have to travel the same distance from here to there and from here to there. So they will wibble the same number of times. So they will be in phase. So on this screen, what we will observe is a central bright fringe, followed by dark fringes, followed by more bright fringes, followed by more dark fringes, and so on. And you'll see that the central bright is the widest one and the most intense one, and then they get less intense and smaller the further away they go out from the central bright fringe. Now we are going to use an equation W sine theta equals m lambda, where W is the slit width. Sine theta comes from the angle that the fringe, the location of the fringe makes with the center of the slit here. M is the order of the dark fringe, and lambda is the wavelength of light. So m equals 1 is the first dark fringe. M equals 2 is the second dark fringe. And that happens symmetrically on either side. So we call this m equals -1 m equals -2. But this equation predicts the location of dark fringes for single-slit diffraction. Now remember that to go back and forth between constructive and destructive, all we have to do is add half a wavelength. So if we want to predict bright fringes, we'll say W sine theta equals m plus 1/2 times lambda. So here we're summarizing things. Location of dark fringes is given by W sine theta equals m lambda, and that means that the location of bright fringes can be found by adding half a wavelength. Now Young's double slit experiment, that has to do with the interference between the two diffraction patterns from each individual slit. So it looks like this. Now I have two different slits, no longer just one. I have a screen over here, and what happens is that we get a diffraction pattern. In my case, I drew it really, really big, followed by a fringe, followed by another diffraction pattern on either side, but within each diffraction pattern there's going to be interference. And that's what all these little tiny M's here say. So right across from the center of the slits, we have M equals 0. And that right there is the central bright fringe for interference. Then we have a small dark fringe. Then we have another small M equals 1 fringe, bright fringe, and then followed by another dark fringe, and so on. So the blue lines here are bright interference fringes, and the spaces are the dark fringes. Now, this entire line here is what before, for the single slit diffraction, we had as the central bright fringe. But now there is interference inside, and the important thing to remember is that all of the fringes have the same size. With diffraction, we had the large central bright followed by smaller fringes on either side. With interference, all of the fringes have the same size. Some other things that I wrote on here are y, so that's the distance from one particular fringe to the principal axis, to the center here. Capital D is the distance from the screen to the slits, and using trig, we can say that tangent theta is y divided by d. We can use small angular approximation and say that sine theta approximately equals tangent theta approximately equals theta. So we can go into a lot more depth with this, but that's really not necessary at this point. So the equation that we have for Young's double slit experiment for the double slit interference is d sine theta equals m lambda, where d is the separation between the slits. Sine theta, theta is the angle that a particular fringe of a particular order makes with the center of the slits, and that equals to m, that particular order that we found at angle theta, of a bright fringe times lambda. So remember, with single slit diffraction, we used an equation that was very similar to this, but we predicted dark fringes. With the interference equation for Young's double slit experiment, we're predicting bright fringes using this equation. So of course, if you want to find dark fringes, then you add half a wavelength. So here I'm summarizing this. So the location of bright fringes is given by that equation, and it follows that the location of the dark fringes can be found by adding half a wavelength. A diffraction grating is a series of slits that looks like this. So with the single slit diffraction, we had one slit. With Young's double slit, we had two slits. Now we have a multitude of slits, and I only have 1, 2, 3, 4, 5 here, but there are lots and lots of them. And now we call the slit separation D. And what happens in this case is we have light coming in through each of the slits, and it strikes the screen, but since there are so many different sources, they can interfere destructively more readily than they can interfere constructively. So there are fewer fringes and further between with diffraction grading. So I have one bright fringe here, and that corresponds to m equals 0. We have a second bright fringe that corresponds to m equals 1, and the same thing on the other side. And there may be another one like very far away, somewhere here or somewhere there, and then they spread out a lot more the further away we go. So with the diffraction grading, we get fewer fringes, and they are much smaller than what we saw with single slit or double slit. The equation for predicting the bright fringes is d sine theta equals m lambda. So it's the same equation that we had for Young's double slit experiment, and just like for the double slit experiment, we predicted bright fringes. So this equation again is for bright fringes. So location of bright fringes can be given by that equation. We can find the location of the dark fringes by adding half a wavelength, and that is a little bit iffier because my statement here is a little bit iffier because by adding half a wavelength, actually the range of angles is quite large. Let me go back to the previous slide. So anywhere between here and there, the angle is going to be between there and anywhere here, angle is kind of large. So this gets a little bit more complicated. Another type of diffraction is X-ray diffraction. So here we have a crystal lattice of lattice separation d. So it looks like something like this, and then when light strikes it, maybe it will really bump right against an atom, but it can also pass through, all the way through, so then maybe it'll bump against this one and reflect. So we would compare the path length of this beam with the path length of that beam. And since this is all really, really tiny, so the lattice spacing is about 1 angstrom, 10 to the negative 10 meters, then the lattice separation here, these angles are really, really small, so we can say that this wave travels twice the lattice spacing more than this wave. So for X-ray diffraction, we need to remember that the scattering is off a crystal lattice. Then we have thin film interference. So the light reflects off the top and bottom surfaces of a thin film, and they can interfere constructively or destructively. So here we have a thin film, and that can be on top of some surface here. So this is something else, another layer under the thin film. And let's say that we have air up here, so N1 equals 1 for air. Then we have an index of refraction N2 for the thin film. And then we have some other material N3. So a beam of light strikes the top surface of the thin film and it reflects. And then it passes through, it refracts through the thin film, it reflects here, and then it refracts again. And these two beams are meant to be parallel, not so much in my drawing, but the path that this beam takes versus the path that that beam takes is just like we had with X-ray diffraction, smaller by twice the lattice spacing than this beam. So this beam travels twice the lattice spacing less than this beam. And we can call this L. So we'll say that the path that the second beam takes is 2 times L. So the first beam travels 2L less than the second beam that I drew here, the beam that reflects off the bottom of the surface. So then, based on the thin film thickness, this thickness over here, this beam can pick up half a wavelength or a quarter wavelength or not at all or an entire wavelength. So we don't know if this beam and that beam will be in phase with one another or out of phase with one another when they reflect off the top and bottom surface of the thin film. Then we have polarization. Polarization has to do with the orientation of the electric fields in the electromagnetic waves. There is something called plane polarized light, and for that, if the orientation of the electric field is random, then we call that unpolarized light, and we draw that like this. So this is unpolarized because the electric fields are pointing every which way. So E has directions in all kinds of directions, whereas with polarized light, the electric field will be polarized in just one direction. So we could have an electric field going this way, or we can have one going that way, but it's only in one direction, not like we saw with the previous one where the light was unpolarized. Then we have circular polarization, where while the electric fields have uniform amplitude, they are constantly changing direction, and they obtain this helical appearance. So that's what we call circular polarization, and some of that is used on phone screens, so that when you look through a polarizer, your image doesn't disappear altogether, but it just changes colors.